Okay, so since we're running low on time, I'll start all the way in the beginning. A lot of you are probably familiar with functional magnetic resonance imaging, fMRI, and basically I just wanted to kind of underline the point that a lot of people have underlined right before me, that these are high-dimensional data sets, right? We have millimeter spatial resolution, so hundreds of thousands of voxels, thousands of frames per single scans for single subjects, and dealing with this has been a statistical journey. So, right, the original work kind of starting with general linear models, very solid statistical founding. And right, these analyses were very easy to tailor to the hypothesis you wanted to answer. It was very easy to generate the hypothesis question, create the design matrix, and then use your data to find the, run the regression that you wanted to run. And these methods were per voxel, right? So there were univariate regressions. You could model the time covariance, but there wasn't any spatial structure. And so as we're learning more and more, right, neural codes are spatially distributed as well as temporally distributed. And so we needed a way to take care of that. So next on our journey was multivariate pattern analysis, MVPA. So a lot of tools like we saw just a few talks ago, utilizing a lot of the statistical and machine learning methodologies. And kind of the big jump here was moving from a generative modeling framework to more of a discriminative methodology. And so the hypotheses were a little bit looser, right? It was more along the lines of voxels contain label information, for example. Can we do classification? Can we do prediction using our data? And so, for example, this is a very nice picture from Husser et al. Just last year, showing a figure of how we can infer structure in the frame that was shown to the subject from the brain activity. And so kind of what we gained was we were able to suddenly utilize the spatial information that was unusable before. What we lost was that inference was more difficult and less easy to interpret. So can we have the best of both worlds? Can we have the interpretability, the statistical grounding, and the hypothesis-specific analysis that we'd like, with the ability to do what MVPA can do, which is to really utilize the spatial information? And so what we've been working on is a way to kind of take a lot of these analyses that people have been using, so ISFC, joint modeling, RSA, BRSA, shared response modeling, and kind of put them under the umbrella that would let us do both of these things as well as we can. And it turns out that the umbrella that we're going to use is what's called matrix normal models. So how does this work? So the first piece is to write down a generative model that captures all of this structure. So our data per subject Y is a combination of a spatial projection. So there's three terms that we're going to parse out. So the first term is going to have a latent time course projected through a series of spatial projections that are, so the latent time course would be subject independent, the spatial projections would be subject dependent. So these are the types of terms that we would see in analyses such as shared response modeling. There's a second term that is the effects of the design, the experimental design. So this is the regression, the spatial regressors, and the design matrix that we're normally used to seeing in analyses such as RSA. And the structured spatial covariance residual that kind of accounts for the rest of the model. So the second piece is how we actually create that residual structure so that we can do analysis in an efficient way. And so this is where a lot of assumptions come into play. In particular, the assumptions that we pick are to use what's called a Kronecker separable residual. And so what this means is that the covariance of the residual in time is independent of space. The covariance in space is independent of time. And so rather than inferring this gigantic covariance matrix of their entire data set, we only have to infer the structure in kind of these two separate data sets. So this is a little bit more restrictive than some of the other residual modeling techniques that are around, but this will allow us to really apply a lot of these methods to larger data sets efficiently. So with these two pieces, I'll give a couple examples of how we can write down these models. So for example, we can take representational similarity analysis. the goal of this analysis is to find the second order information of the regressors. So, right, so we want to find these regression coefficients B, and actually more specifically, we want to find the covariance of these. We want to know how these regressors interact. And so rather than doing what RSA typically does, which is to estimate B, right, regress onto B, and then find a covariance matrix, we can actually write down the likelihood, write down a prior over B that includes the covariance, and then solve a maximum likelihood directly, because we can marginalize over B using the properties, right, really nice properties of Gaussian distributions. So we can compare to traditional RSA, and more specifically we compare to a recent version of RSA called Bayesian RSA, which eliminates some of the bias in the original RSA analysis. And what we found was that the spatial and temporal covariance structure actually lets us, for larger data sets, infer, in this case, synthetic data more accurately. So in this plot we see for different sizes of data, so voxels ranging from 400 to 1,000 or 10,000, and different levels of SNR as the different rows, and different numbers of regressors as the 3 data points per plot. And so for more voxels and across pretty much all SNRs, we perform better in terms of the root mean squared error. Additionally, we have a 10 times speed up utilizing the properties of the Gaussian modeling that allow us to pull a lot of computational tricks. So since I have a little bit of time left, I'll just run through a second example, shared response mapping. If you'd like to see this in more detail, stop by the poster that I'll have. So this is taking the other terms, right? So this is taking the latent time course and the per subject spatial map. And we would like to learn what both of these are. We'd like to learn the subject independent time course and the spatial map. And so we can again utilize the properties of Gaussian distributions to marginalize over some of the variables. So for example, we can marginalize over the spatial maps, learn one single time course for all subjects, and then go back and regress out the original, the F matrices, these spatial maps. And so we've tested this on a number of data sets, so both the Radar and Sherlock movies, looking at whether or not we can train this model, we can learn this model using our regression technique on a number of subjects, and then predict the activity of held out subjects. And so just at a glance, if you look at the root mean squared error, our root mean squared errors are typically lower than some of the competing methods, including the original SRM methodology. Again, just for the sake of time, I can go in that more detail at the poster for anyone who's interested. So a couple other methods that we can that kind of fall into this paradigm is topographic factor analysis, intersubject functional connectivity, general and regular canonical correlation analysis, probabilistic PCA. These are all basically fundamentally Gaussian regression models if you know how to write down the model the right way. So just to finally top it off, one of the benefits of putting all these models together is that it allows you to make an efficient coding package that lets you switch between the different assumptions on the regression. So whether or not your temporal covariance is AR or independent, whether or not you have a Gaussian process covariance for your spatial maps. And we've created in the Brainiac toolkit a kind of package that lets you switch between all of these and efficiently utilize the properties of the Gaussian distribution to do automatic marginalization, flexible covariance selection, and this will allow for just very easy prototyping if you're not sure which model to use. So just to recap, we presented kind of a model for matrix normal model for fMRI data that kind of encompasses many of the analyses that you're used to and use already. And we've used this kind of modeling methodology to create a toolkit that lets you really try out these different methods efficiently and quickly, utilizing the latest in the automatic differentiation and machine learning toolkits. So with that, I'd if we have time for questions, I'd be happy to take any. Otherwise, I will see you at the posters.